started now. I think we're online. Okay, so what I'll kind of show you, I really want to get here this afternoon, and this is, I haven't uploaded this because a lot of these modules are kind of in the process of working. And also remember, Marina introduced us to this world of OSM extractions. And anyway, so I'm trying to get these Uber trajectories, which we will see maybe next hour or right after lunch, working on the San Francisco maps. It's a Uber in San Francisco. But yeah, there's a lot of technical issues because if the map is too big, the driver crashes in the community edition, and it's a lot of engineering problems. And on top of that, there's Java versioning issues. Magellan has drifted off in a different direction, so we're sort of building these custom jars for Magellan. And anyway, I will sort of point out that there's all this stuff like this, and I will just upload it as is. Maybe the Kiwis will fix it before they go to bed at midnight. Let's see what happens. If not, it's okay. We can still conceptually get everything, and the code can be fielded. Okay, so it's a lot of errors. Okay, so today we'll continue with sort of where we left off yesterday. So you guys will have a lot more notebooks here, right? Yeah. So I just moved mine. So you will, for example, have 21, right? Yeah. So I just moved mine to today because it's today for me, but okay. But today isn't finished, so it's the same exact notebook. Okay. Am I okay sound-wise, Tom? Okay, perfect. So I thought we should kind of look into this because we're going to study trajectories in more detail soon. So trajectories, you know, have you know, the Microsoft research papers, which I will link in a sec. But the main papers we are sort of diving into, so I'm kind of introduced myself into this world, is this paper called Urban Computing. I highly recommend it. You know, a lot of the concepts that, yeah, I mean, I'll just show you the pictures at least. A lot of the concepts that John talked about yesterday, from the view of Microsoft research, having lots of sensors and cloud and blah, blah, blah. A lot of computer scientists, they kind of package it in this way, which is essentially the same problem. So you have whatever, people, cities, and environment, and you have whatever, lots of challenges, right? There is pollution and urban data analytics, urban planning. And you have urban sensing and data acquisition. In fact, there is a Uppsala IoT group here. Professor Nye, I think, she has a group that's collecting data, sensor data for Uppsala, like Uppsala Smart City project. I think it's supposed to conclude soon, and everyone is supposed to have access to the data. And I was sort of doing Google searches, so I couldn't find any yet. But then we can just plug into Uppsala's smart city sensors. So this is what's happening. Some cities are really ahead. Some others are starting. Okay, so you have traffic lights, whatever, anything that can be shared, bike sharing data, you know, depending on the type of city, like Chicago and New York are open cities, open data cities. They share all their data on, you know, telephone emergency calls made to emergency services. It's all streaming at you, right? So you can integrate a lot. Weather, blah, blah, blah. So anyway, I you know, if you want to read it, but I'm kind of coming at it from this particular paper, right? And what in urban computing, of course, it's city focused, but it has this amazing data fusion problem. So you have data from completely different domains, and you have to somehow fuse it in a way that allows you to take what people in the business world call, what is it called? Actionable insights. So it empowers a decision maker to actually take an action in an informed way. And that's kind of where, like, this R&D company I was working at, that's kind of was our sort of main domain. We could kind of allow this kind of intelligent data fusion. This is a great paper, and this is in fact the data I'm trying to break you guys on. You know, this is Beijing's trajectories. This is actually Beijing. And we just grabbed the OpenStreetMaps, and Microsoft did this really detailed study on trajectories in Beijing for, I think it was it's a lot of trajectories. I forgot. It was a month of very detailed taxi trajectories. And you can do quite a lot with this. So these are spatiotemporal trajectories because there's timestamps and then GPS locations, right? That's a point in 3 dimensions, time and long lat. But then it also has the ID of the taxi minimally, typically, right? So this becomes this ID specific, you know, trajectory, like John showed those pictures. Those are spatiotemporal trajectories, and there is a whole lot of computer science data structures specifically designed to deal with spatial trajectories, spatiotemporal trajectories, identifiable spatiotemporal trajectories, and sort of the structures of spatiotemporal trajectories. In fact, if you just search for topological invariance, big data, blah, 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 there's a lot of math topologists and, I don't know, computational homology, I don't know, all these more mathy people that do computations are also getting in the game because there are very nice invariants of the structures of these trajectories that can become very nice statistics. Statistics is just a many-to-one mapping of the raw data, right? It's a measurable mapping, so you could have, you know, anything you want. So that's kind of like 2 months old research, but this is kind of where I started, which is like almost 6 years old. And what is the main idea here? They start fusing things. You know, yeah, so they combine mobility data, cell phones, blah, blah, blah. And these blocks are essentially this sort of statistics, socioeconomic statistics that John was talking about that's available to him at a yearly resolution. So, and when we were doing burglary prediction, for, you know, anticipating where burglary events are likely to occur based on the past patterns of burglary reoccurrences, we started basically doing things on networks, on 3D networks in some sense, right? Because for us, every address in Manhattan or wherever is a location, is a node on a graph that's sitting on space and into, you know, if it's a building going up. So these are all opportunities for burglary, right? So these are kind of the structures you want to have in mind. And the nice thing is it's all really nicely visualizable. It's usually in 3D or moving pictures in 3D. Okay. Urban computing for transportation systems. So once again, to take a lot of stuff John talked about and just sync it into current data structures, blah, 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 arithmetics, algorithms. This is a really good one as well. So in fact, IBM research in the latest Spark Summit talked about how to fuse weather data with real-time traffic data. And again, I try to get this to you guys. This is too much. There's something called open traffic. But you know, I haven't still heard back from them. So they have an API. So people just voluntarily submit their GPS coordinates to this organization. It's non-profit. It confidentializes it somehow. It's all over the world. So then anyone can tap into this API and see sort of traffic in motion, which you can ingest into your other systems. So you could kind of, you know. So anyway, I still haven't gotten the token for us to play here. So we'll just use some old data for now. Okay. Yeah, so this is another one. Yeah, so this is basically Uber, right? This is Uber's idea before Uber, dynamic taxi ride sharing. All right, what else is important? Air quality monitoring. This is a huge problem for Beijing. So, you know, the basic idea is that you can somehow dynamically give incentives for taxis and you know, enforce ride-sharing rules based on the current wind conditions and pollution levels by real-time sensing. And that's this is, you know, already 6-7 years old. So this is kind of what you know, one could do, right? Because in Paris, when the air quality like really drops, right, you get like free rides on all the public transport, which I didn't understand. I freaked out. Oh, my car isn't working. Oh, It doesn't say I'll just go through. You just can walk through. The thing will roll, right? So anyway, that's another simple model, but this one's a bit more noise pollution and blah blah blah, right? This one I thought was actually, I read this paper in a bit of detail. So here they're talking about crowd sensing urban refueling behavior with GPS equipped taxis, right? So you can essentially anticipate queue lines and stuff like this, right? So it's kind of operations research mixed in with real-time ingestions and stuff. Okay, so I kind of want you guys to think about these pictures, because that's kind of the later part of this today. I will get you to hopefully to operators that will represent roadways like this as Markov chains. So for example, what I mean is, see, we can take each road segment between junctions to be a state, okay, of a Markov chain, like a lily pad, and each junction to be another state, right? So if the taxi, sort of goes from here to here to here in my sort of discrete time clock, say every second or whatever I'm monitoring, then this frog will jump from this lily pad back here, back here, back here, and then it'll move here, and then it'll move here, maybe here, and so on, right? So we have this nice projection of the continuous time car movements into a discrete state representation of the roadways, right? And so I'll kind of get you guys there. I've told you a lot about distributed linear algebra. The sort of next steps to essentially start publishing papers with John and Marina, they tell me, is just doing a little bit of arithmetic, right, with real data. But we may not get to that today, okay? What else is here? Yeah, so these are also, again, in sort of Microsoft Research lingo, we can reparse it back to what John was talking about. So you have locations and you have users, and people go to various cafes, and then you can start associating, mapping users to locations and things like this. So if you, for example, did anyone read David, Data and Goliath? Okay, you started reading? Okay. So there are commodity brokers out there that'll sell this kind of information about a user, and that kind of information can be used by various other third parties that'll maybe try and find a nice date for you or something. I mean, this is kind of happening, right? This is not like this is old stuff. So how is this possible? You say, I don't have anything in my cell phone. I turn off all the apps, but I mentioned this before, like, I don't know how many of you play free video games, free apps games in your cell phone, like Angry Birds. I don't know if Angry Birds still. So anyway, this is what David talks about. He says, like, a lot of these free apps simply send very minimal information. They will not, and the minimal information can be as simple as, your battery charge level or whatever. I forgot all the details. He talks about it. And so, that's kind of enough coupled with some wireless location information to like kind of give, these uncertainty zones around where your most probable location sphere is. It's quite a lot of information. You can fuse that. You can hit that with cafes or nightclubs or whatever, prostitution centers. I have no idea. You can do all kinds of things to actually find information about people. And when you start fusing that with so many other sources, you can do quite a lot of things. So there's a whole branch of research, again, not just MSR, lots of people in computer science and social computing or web computing, whatever they call this. That's all about these kinds of, getting bipartite graphs. And anyway, maybe I should stop blabbering too much, but I recommend this one. Actually, this paper is brilliant. So this one we read in a lot of detail. So you're now trying to detect anomalies from urban traffic based on distance. This is the Manhattan one, I think. So yeah, what you want to do is anticipate where the urban traffic congestions are going to happen. And so in this one, I think, they basically, oh no, sorry, this is not the paper. So anyway, this is one subset of, so this other paper, they were sort of ingesting also social media feeds from people frustrated in traffic, like Twitter. They'd be like, and so they would use lat long boxes for geolocated tweets in that region, have that as one stream coming in, and then they also have the emergency telephone services in Manhattan coming in, and then they have the bike sharing data coming in, like people not getting to bikes on anticipated time. So they fused all of this to essentially anticipate congestions and, I don't know, some kind of urban. Yeah, let's see. Let's stop at the next bright pictures. It's a lot going on. Yeah, so this is just check-in data. Yeah, I read this paper in 2016, so it's all a bit murky for me. Okay. For the graph theories people here, so what happens is, so you will have these trajectories on very large graphs, but then remember our linear regression or gradient boosted regression trees we did, those guys need a feature vector space, right? I mean, they usually need some kind of, points in some Euclidean space, some real vectors. So there's a lot of research done. There's a NIPS paper that is in one of the links done by someone from IBM just a few months ago in one of the Spark summits. And that NIPS paper talks about two basic kinds of graph embeddings into metric space. So what that means is you have a very large graph and you have some kind of trajectories moving around somewhere. And you want to use that, this is multiple co-trajectories, so it'll be lots of traffic and whatever. So you want to use those co-trajectories and the local road network structure that they're moving on to essentially anticipate, some kind of congestion or time it'll take to travel from point A to point B through this sort of mess. Then, the two main types of embeddings, this other group did, I don't know from where, they talk about local embedding, so which essentially looks at a random walk on the graph, but restricted to, the local neighborhood. So this is very related to a Markov chain, a local, a Markov chain where you start somewhere in here, but don't let the walker go too far, basically. So you can essentially represent this local information using this embedding. And then the other one somehow accounts for long distance. So I haven't read the paper. I'm just citing from 45 seconds in that video. But it's all there for you. And so what I hope you'll get out of all this is that you have all these opportunities to actually put things together, because we can't do everything in just one day, or 2 days. So, but you will essentially have all the basic tools to do this. And they also do the deep learning, long short-term memory, which is, again, another regressor, basically. So, all right, what is all this? Some matrix multiplications and tensor. So there's a lot of tensor decomposition. This is a three-dimensional matrix. All right, I'll shut up. This is a long paper. So then the other paper, I think, setting the stage here is... So this is kind of my lecture sort of overloading on John and Marina's lecture, right? So I'm not an expert in any of this stuff, so I just, kind of recommend reading these papers. This one's quite good because I told you I'm into tree arithmetic, so it's kind of closer to my own research area. So this one talks about, sort of how to mine trajectories, how to look for patterns, how to classify trajectories, how to detect outliers in trajectories. If you recall, that's exactly a lot of the problems John was talking about, right? I mean, so anyway, I won't get into this. Moral of the story, read what has been done before you roll your own, Okay, so let's get into today's content. Yeah, of course, I don't want to. So, has anyone read the Joint Operating Environment Report, Joe 2010? Oh man, I would never send my great granddaughters to space with your great grandsons. Okay, so that's a joke. So so in Joe, what the Americans are really saying, and then pretty much all the agencies across all the big countries, they agree, is that what's going to happen, what's already happening, is that the knowledge that is inside one specific domain will get so specialized that there will be like some other incredible amount of knowledge in another sort of different domain That's super specialized. But then the slightest fusion of that knowledge will lead to completely unpredictable things. And in fact, that's one of the hopes that they have for humanity, basically, right? So I mean, I don't know, in the US and India as well, like India's pumping tons of money into pure maths, finally, 60 some years after independence, because it's all engineering and statistics before, right? Believe it or not, India is a good place to do pure maths now. So US strategy is very clear. The US National Science Foundation, as well as the Society for Industrial and Applied Mathematics, they are strongly recommending the programs be highly, I don't know, so mathematicians should code more. I mean, not just learn coding from people like me. I'm just like, you know, learn coding from computer scientists, you know. So that's very important to give strong foundations by experts so that they have the skills to keep learning, right? And this is what Andrew Nick talks about too, right? It's also what entrepreneurs talk about. So although these papers are there, often, you know, maybe people in John and Marina's world, I don't know how much of this really reaches their sort of. Is this true, John? I mean, this kind of Microsoft research, this is more computer science-y.
Yes.
It doesn't reach your, I don't know what cultural.
No,
yeah.
Sort of very isolated.
Yeah, exactly. So these are like little different clades in this sort of geospatial learning tree or research tree, right? And that's kind of the. Anyway, so this is let's get to Mira. I really like her. I just saw her on video, so. But I'll just play the first couple minutes. And
well, thank you. Okay, today's talk is about IoT time series and prediction with Android, Spark, and Cassandra. But before starting, I just want to warn you. You may hear some awkward words during the presentation. Don't worry, it's only my French came up sometimes. So my name is Amira. I am an agile Java developer at Tech. I code in Scala in my free time too. And in spite of coding, I'm also a runner addict. I started 2 years ago, and my challenge for this year is to do my first marathon race at Atlantis. So wish me luck. You can follow me on Twitter if you would like to hear some tech news, and all the code of this presentation will be available on my Twitter. I'm also one of the Duchesse France leaders. Duchesse France is an association aiming to promote a female profile, to give them more visibility and also create a technical vocation among girls. So we always need support from the IT community. Follow us on Twitter and help on our blog. IoT, the Internet of Things. When I started doing my researches about IoT, I was wondering where all this has begun. And while doing my researches, I found an interesting report of this field. The report shows the increasing number of population and the meantime the increasing number of connected devices. And according to this report, IoT was born between 2008 and 2009, when the number of the connected devices exceeded the number of persons on Earth. Amazing. Today we are about 7.2 billion people on Earth, and each one of you had at least 3 connected devices. And this number is going to increase incredibly the next years. We may reach 50 billion of connected devices in 2020. Amazing, huh? So imagine this network of connected devices, from wireless connection to the internet, from embedded system to the electromechanical system. All these contribute to the internet of things. And all these systems are capturing a huge amount of data.
All right, let's sort of cut to all this, Chase. So she's doing this amazing engineeringly complex system where she uses. So, you know, basically her friends collect data for her in their cell phones, and they give her the. So one of her buddies like does this for a while and gives her data on jogging. Right? What's the data? It's the accelerometer data and timestamp. Right? So how much I accelerate in X and Y and Z, whatever. right? So that's the raw data, timestamp and accelerometer XYZ measurements, and of course it's like every 5 seconds or something, or every few seconds, and then and then maybe the same person just sits. So his activity is sitting, or jogging, or running, or standing, and stuff like this. And a whole bunch of her friends do it, maybe 6 or 10. So then what she's trying to do is use this information to predict the activity in the future, or what they're doing right now, what they're about to do in the next second, basically. And so we will basically look at, I kind of simplified her code a lot. She's doing a lot more, but and then she's also using Cassandra, which is this key value store that comes from, is it Facebook? Yeah, Cassandra is Facebook, right? I think so. Anyway, so she's using a lot more of the big data ecosystem, around Spark, and not just Spark, but we're sort of not engineers. And what she's trying to show in the end, I wanted to show, is like how her app really works. That's kind of what so she's here showing it in action.
I created my pictures, which is used to create my library point and even to predict. So here we go. We're going to start our prediction server.
So she's deployed it, and
as you see, your streaming has been started. So it's already been streaming the latest data from Cassandra. And now I'm going to push the start button. And now here you start seeing the accelerometers, real-time data. And then you're going to have our prediction. I'll be standing. I'm not joking. Standing, great. Now, if I'm sitting, so the phone will be like here if I'm sitting. Or no. Sitting, great. And I'll be walking. Walking. Oh, nice. And maybe some jogging. Some morning jogging. Here we go. No jogging. No, it doesn't want. Jogging.
Anyway, I thought that was cute, right? I don't want to take credit for this. I'm just like Scala. I'm just making a Scala version of her Java RDDs, okay? But she also gave me permission to anonymize her friends' names and things like that. So, okay. So this is a very generic framework, because we saw gradient boosted regression trees and random forests yesterday in a static setting. Now we're going to see this in a dynamic time series setting, right? Okay, so now the first thing we have to do is to get this data loaded. So, we have to go to the download and load data first section, all the way in the bottom. It's easiest to just search. So it's probably some wget or curl call to somewhere. This one. So so are you guys able to fetch it and load it? Okay. Okay, so I'll just sort of walk you through these stuff. You can control enter. I may not. So yeah, once you have loaded it into the distributed file system, you should be able to create this data. Then you know, just taking 5 and seeing what it looks like. Ooh. Sorry? Yeah. Yeah, also my network's connection is pretty, Chrome is having a fit. Maybe it'll be okay. Yeah, so, you know, if you see you have user ID, I just kind of removed her first names of her friends, and activity jumping timestamp as long, X, Y, and Z accelerometer measurements. Okay, so as you can see, the millisecond is going from 06 to 71, so it looks like roughly about a second, right? Oh, no, yeah. It's about, we'll see actually. So then the data is here. I mean, the main point here is that the timestamps are regular. So we can just, you know, there's some set time scale. And then I basically am using SQL context read method, which we've seen before. You can use it this way. There's another way to call using the Spark method directly. But this should load us a data frame called data capital DF. And if I print schema, because I've asked it to infer the schema automatically, it's made my user ID as a string, activity as a string, double as a string. What's going on with Chrome here? Is everyone able to get to this and display the data frame? No?
No. When you download the data, you need to add this data training.
Oh yeah, that means this. Have you gone down and have you got it?
No.
Let's see. Maybe there's some. So you did that. Can you show list what's in the file system? Oh, no. This one. Okay, now this will be back because you already did it. So you move the file, so you remove it. So you have to doubly get it again. I just wanted to see what this. Okay. Make sure that this name is the same. Maybe.
Yeah, you copy it too. You need to copy the name as well.
Okay.
Otherwise, you
mean the data training .csv?
Yeah, whatever I'm calling upstairs. Yeah, probably. This is good exercise. I want to click. So you know, you need to make sure that this data exists. So there's probably some name change you need. Let's see. So I mean, what am I calling? Yeah. So sorry. So you know, this name should be there. So I think that name is missing out of the DBFS copy path below. Control C. So probably need this. Yes, I'm moving it, so I probably need this. Is this what you meant? Yeah, so this should work, and then you should see, yeah, you should see this. So, is everyone else okay? All right. My cluster is still going, so so now you guys should be able to see this data frame display, right? You guys are here, everyone? Okay, good. So that's basically our data we're going to mine. And Mariama was asking yesterday some problem in her world, which is simulation intensive biochemical modeling. I don't know what it is. She does something with protein folding, blah, blah, blah. And so she was suggesting that she has this experiments, or her friend does, and then they have a lot of features, you know, and then instead of activity, they have some kind of environment, like how much pH or whatever, some kind of experimental condition or environment. And I don't know. So and she, you know, as a time series as well, and based on the, you know, the behavior of these features, she wants to be able to predict the environment of future data, which don't come with the labels. Is that right? Something. Well, anyway, I don't want to force this in, but this is a very generic framework. This is actually, you know, because it has a Markov aspect to it. So you can look into the past and bring that into the future, and that's what we'll do. So you should have 13,679 events. Now what I'm going to do is just select the user ID. Yeah.
I've downloaded it. I'm loaded it, but still for command 6, like for command 5, it's not recognizing that.
Yeah.
It's like a file. So I downloaded it.
Well, yeah. So there's many things that can be. Let's see what you've done. So can you just show me the display what's in your distributed file store? Yeah. Can you just hit this command? Show me what's in there. Okay. So you haven't done what I suggested. You have to copy the CSV file. Yeah. This has to also be here. Like this data training. You have to re-download. No. No?
See, everything is in the file called the training definition.
Okay. So if you just but that's so just sort of you have to redo it because you moved it. So just double it. No, you're right, but then I have to change upstairs. Yeah, I know. Well, I'm here. I don't want to come back. Yeah. Are you set? I mean, these are like basic things, right, from your previous homework assignments. So now you should see. Yeah. No. Yeah. It should have this file called data training. Yeah. All right. But I mean, you know, we're sort of going to get collectively slowed, and that's okay, you know. So anyway, here is the user ID.distinct show, and we have, you know, these users. So we have 1 through 7. And then I'm basically just looking at what the activities are: sitting, walking, jumping, standing, and jogging. And, you know, of course, my commands won't work. That's okay. Right, so, and then here is my data frame. I'm just looking at it as a scatter plot. This is, as usual, very important. So I'm looking at the marginal densities of the accelerometers along z, y, and x. And if I make this tiny bit smaller, and I'm showing you all the pairwise scatter plots in these colors. And, you know, staring at it, this really sticks out, right? The green chunk here, y and z, is quite concentrated. And, you know, just really bang on 0, right? So let's make sure this, yeah, it's 0. So, yeah, this is a very strong pattern, but other things are more spread out. You know, jogging seems to be, you know, much more dispersed than walking, which makes sense. You sort of accelerate. But, you know, there's sort of XY specific movements as well that gets picked up on certain. Okay, so there's a lot of information in the data. It's kind of what you should do, right? If all the data points is on 1, 0, 0, something else is going on. So anyway, once that's there, now we're going to make this very simple Markov assumption. So we're going to do feature selection on running windows, right? So the idea is that we have time, order data, and then we will sort of order it by user and activity specifically, and then we'll have this sort of moving window, a running window, and then what we're going to do is this sort of Markov assumption, right? So what's a Markov assumption? This is so the general idea of a Markov process is this. So we're interested in predicting some variable x, a random vector, random variable, it can be a random graph, some random object, as a function of time t, right? So typically time can be either discrete, so that means it starts at 0 and keeps going, So we can think of our data as discrete time because it's in regular intervals. We don't really have to get in there. But time could also be in the real line, right? So it could be 0, infinity. So this is if you have like atomic clock or something. But for us, t is discrete. So actually, for that, let's make time to be k. This is k, it's discrete. So what we have is this process. So this is now a sequence, and k can go from 0 to infinity or whatever, some big n, let's say. So we observe it for capital N many steps, and then what is going to be the probability of this? So the probability of this long vector of length n taking specific values. So let's say this takes very specific values, and usually in notation you say this is lowercase of x of k, and this is k going from 0 to n minus 1. So the probability that this random object takes this realization, this is an event, we'll see all this later formally. This is going to be given by the probability that, well, okay, if you break it down, it'll be what's called the joint probability. So it's this happening and that happening and that happening. But then if it's a Markov process, and in the simplest one, you will say this is the probability that x of k, let's see, x of n minus 1 equaling, so we'll give x of n minus 1 given x of n minus 2 taking some value. So these all have realizations, times the probability that xn minus 2 takes some value given x minus 3 and so on. So then you basically simplify this as a multiplication operation as k goes from whatever, let's say 1 to n minus 1, and k, I don't know, I'm going to be pretty sloppy. I am really prepared to do this one. K equals, so probably k plus 1 given k, and something like this. Okay, and then finally you have to multiply by the initial condition. So what is the probability that x of k equals x of 0 equals some realization, right? So that's kind of the idea. So you can break down something very complex, fully structured thing, into pieces. So what happens the next time step only depends on the current state, and what happened in the current state only depends on the previous state, and so on. That's generally the Markov assumption. And the Markov assumption is incredibly general. It doesn't have to just involve time. It can involve graphs, and so it can be, if you're looking at some kind of a process on some graph, say random walk, like which we will come to soon. So there, once again, you have a random walker, he's here, or a frog, and then it goes here or here with probability, say 1/3 and 2/3. Then, what is going to happen at the next time step only depends on the current state, right? Because of this local structure, right? And once again, Markov can be not just in time; it can be in but the main point is we don't have to worry about what happened in its entire history. Where was the frog like 2 steps ago is irrelevant.
Just one quick,
yeah.
What do you mean by sort of equality that there is x it's not reals, right? It's on a mesh or something, because if we have equality, would we have a probability 0?
What did I do? Yeah, I think so. No. I'm just okay. This is really too much. It's okay. It's much simpler. So, did I make a mistake?
No, probably not. But I don't understand.
Yeah, this is bad. I'm sort of pitching at those guys at the same time. Okay, this is really trivial. All I'm saying is this: I'm just saying, just imagine, you know, I don't know. Yeah, okay, let's imagine the frog. It's the same problem. So frog is jumping between two lily pads, right? So my state, say if the frog initially at time, I do this x of 0.
If you do that, you have
is at state 1.
Yes, you have just the discrete sort of domain. But I was just thinking if this was, if x was real, then.
Oh, you want this time to, you want the state space to be real? That's delicate.
I don't want to, but I was.
We will never go there in this course. You really need notions of Harris recurrence and hardcore measure theory. We will only make the state space discrete for this thing. But we can make this time continuous in a trivial way. It's called Poissonization. That's no biggie. In fact, we can, that's just like coupling in some exponential clocks ringing independently. But to make the state space continuous, that's a very delicate thing. I mean, I have to go and read like Billingsley myself. I have to read my own grad level textbooks before I lecture, right? I'm very rusty on these because there are more delicate notions of recurrence. And I haven't told you notions of recurrence in finite state stasis, so that's easy. But I mean, I don't want to that's not that important. Just get the intuition that the whole history doesn't matter, right? So and that's exactly what we're doing. We're going to just play around. I played around, she also played around, kind of, and this is what I think she uses as well. So I'm just saying I'm going to use a window size of 10. I'm only going to look at the past 10 timestamps. Okay, so and then I partition by this user ID and activity because and this is kind of the similar problem in predictive maintenance and things like this that a lot of people in industry all over the world are currently focused on. So what happens in predictive maintenance? You have machine sensors on them. They're streaming data to into the cloud or wherever, your local cloud. And you have to see if it will break down in the immediate future so you can send a repairman to fix it before it breaks down. Huge cost savings. It's basically the same problem. So there again, I would partition by user ID and activity. So in the predictive maintenance context, the activity will be functioning, sort of optimally, not so optimally, like red, orange, green, okay, and it's broken. So when it goes to the orange regime, you want to basically stop it remotely and send someone to fix it before it breaks. So it's exactly the same problem, and that again will be user ID specific or sensor ID specific because there are so many sensors in these huge machines or whatever you're monitoring. And you want to have sensor-specific pattern mining, basically. So that's natural. And I want to order by timestamp as long because, you see, I want to have a nice time series structure into it. And then I do rows between minus window size because that only looks at the minus 10 units into the past. Okay, except in the very first thing, there won't be anything, and slowly it'll accrue. And 0 tells me from the current row. Right, look into 10 as far as 10 into the past when possible, and that's basically it. And now we have a window specification, and then we can just do the following. We have data feature df. So we take our data frame. We say with column mean x. I want this to be mean of the column x. Okay, over the window specification. So same, I have a mean y and a mean z. So I'm going to create, with column creates new columns, okay? That's all that does. So these are all from her GitHub I pulled. So she was looking at resultants and I don't know, all kinds of absolute mean deviation and blah, blah, blah. But I try to keep it a lot simpler. But I left all the code here because it's useful for more delicate sensor problems. So you can do square y, square z, resultant, mean resultant, absolute deviation from mean, whatever you want, right? A lot of various statistics of the last 10 measurements. And I wanted to throw in variance and standard deviation, okay? So now we have a whole lot of columns, right? These are just, and note that these new features are summaries of the past. Immediate past at each row. So that's what we're going to use as sort of information into generating these future states. Okay, so now then I'm going to do this. I'm going to do the simplest cross-validation. Remember I said yesterday there is 2 ways of doing cross-validation. So I'm going to just randomly split the array into 70% and 30% with training data and test data. And so then we're going to hit random forests at it, right? So random forests we covered yesterday in a bit of a hurry, but it's essentially an ensemble method that uses a whole bunch of decision trees. Yeah, so one very, very important point. So, sorry, this is a tiny excursion. You know, yesterday we had this discussion about why we are penalizing coefficients in linear regression, right? And I asked Marcus, and Marcus said that's because and Don drew this picture as well. So let's say these are my points. Most of the points are here. And maybe this is kind of, if this point were there, this would be the best fitted line, right? But at this point, especially if it's far away, right, it's going to have this huge square error, right? It's going to really, this is, I think what you were saying is like outliers. So this is going to really make something maybe quite extreme like this. I don't know, especially if it's very up. So we don't want that in some sense. And but note that the slope increases. And the same way, if the outlying point were here, right, you'll get something like this. You know, instead of this one, you're going to get something like this, right? Because this is even more extreme. So, and again, the slope becomes very negative. So when we penalize on the L2 norm, which is basically, you know, how big the slope is squared, then you know, then it won't be, you know, it'll penalize for having a big slope. So maybe it'll bring it like this. But this is an extreme example. But instead of doing this, maybe it'll bring it closer to. So this could be the more penalized line, you know. I think that's kind of the intuition. And you know, when I said, oh well, so I kind of said, no, you have to really look at all these examples. So I want to say where I'm always coming from with regression, and this is like mine. So, you know, when people say they want to do regression, the real thing they're after is actually something more elementary. So they're actually after, so if I have my, let's see. So if I have my, okay, if I have a bunch of points like this, okay, so people say, oh, let's just do this. And then I get a new X that I've not seen before. And I want to predict where y is going to be. So I'll take the slope, and then I use my, because remember, even when we did the simulation, we added this epsilon noise to the line, right? There was basically a Gaussian with epsilon, you know, variance 1 sitting on the line, like a little mound. That's the model, right? So what does this mean? This means that when I want to predict the probability, so I'm not really after the probability of y given x, which is what I really want. But in classical regression, you're after the expectation in the mean value of y given x takes this specific value x. So that's why you go after this slope, right? But that's really a compromise. I mean, what you really are after is the probability of y, you know, or actually if you want to think about it as a densities, which is easier. So this is some kind of. So you're really after the conditional density of y given x. So this is really what you want in some sense. So I want to be able to predict the density itself of y given x. So this is nice because it'll still work in this case. So what you'll return is this little density, but it'll work in some completely crazy cases as well. You know, it can be a very, very complicated function with holes, like guaranteed 0 areas because of some complicated, you know, financial or cyber transaction that simply disallows existence of certain combinations of numbers, right? This is very natural. So if we have very structured densities with a lot of complexity, the mean may make no sense because, you know, if we have something where you definitely cannot have data, and then if I have another set of sort of peacock feathers, right? Like you have a bunch of data here and a bunch of data here. The best linear regression will go right through there, through impossible space, right? So, but this way of doing it will always work, because what it will tell you is, oh, now, let's move this x here. So if I'm interested in this x, let's say there's a lot of points here, it'll give me something like this, and then it'll give me 0 probability there, or whatever, and then it'll give me something like this. It'll create a bumpy thing automatically. Okay, people don't do that because the arithmetic doesn't exist for it, right? I mean, it's not convenient to be able to do that easily, so you can't just anyway, the arithmetic exists, right? It's in my C++ library. It doesn't have any R interface or Python interface, so no one uses it. Anyway, that's a different story. So now let's so we're going to build our transformer just like before. So we have a string indexer, and remember the string indexer is what we use to make sure that our label column is a string. That's how we specify it's a it's a classification problem. This is actually a classification problem that's trained on continuous features from the past. And I have set my input columns to be mean x, mean y, mean z, standard deviation x, y, z. So I played with all these other things Kani throws at us, and I didn't really find we needed resultants and all these things by just staring at the data, because mean of the recent past in each coordinate and just the standard deviation captures everything about these activities, pretty much. So as simplest thing, set output column to be features, and then this is like before. I mean, we now have this random forest classifier, which is another ensemble method like the gradient boosted tree, and we set the number of trees to be 10, and feature subset strategy to be auto. So there's a lot going on. There are. I think in each time, who has a very clear idea of random forest classifier? Yeah. So I mean, it does all these subset selection, right? It ignores some features when it builds one tree in the ensemble, and ignores other features at random when it builds another tree. So it's sort of, I don't know. I think of it as drinking a lot of vodka and building a tree, forgetting a lot, and then drinking some other alcohol, building, which is, in fact, deep neural nets do this, and there's some theory kind of why this works. So then each tree kind of focuses on the strengths of subsets of data somehow, and then when you bring them all together in this sort of way, this ensemble way where you query each tree for what it should be, then it seems to work pretty well. So these are all various parameters. You can play around, and because it's classification, we have to decide where we're going to choose, which dimension we're going to choose to chop, and where in that dimension we're going to choose to chop. Once again, it uses the same measure called Gini impurity, which is, so it tries to find a chop so that, all the colors of the same type, all the activities of the same type are basically in each cell as much as possible. That's the same as a couple weeks ago. Then we said the accuracy, activity, label, and prediction is what we're going to select. And what we're going to do is take our model that we fitted and then transform it. So this will probably take about 5-6 minutes on your community cluster. And then we're going to just transform it with the test data so we can see how well it's predicting, basically. Right? So we select these columns and then filter the prediction. So then our accuracy is basically 98%. So this is not like autonomous driving, so it's good enough. Okay. So I don't know. So this is kind of a little recipe, and remember, this is just one of multiple ensemble methods, and but it's quite a nice thing, and it usually works pretty well. Oh, by the way, my whole point with this is ensemble methods, gradient boosted regression trees, or random forests are all in this original class. They're going after expectation of y given x. They will not be able to go after the density of y given x, especially in complex structures. So they're not like, they're pretty good for lots of problems where that expectation assumption is reasonable. Okay, are you guys happy about this? Okay, good. So anyway, let's see. So maybe the ideal exercise would be to take, something like this, and then later stuff we'll do today, and then maybe you can, when you do stuff in Community Edition, there's the publish button. Have you seen that? So be very careful with Twitter data. Like if you have a display and have someone's Twitter data, don't publish it because it's hard to unpublish. Except that I think pretty much everything I've done is fair game. So, a very simple way to show that you've done the work, some of the work, except Twitter. Twitter you can also show, you can just delete the output cells. If you go and just delete it, it's okay. Is to just publish it and then send me a link with, say, SDS22 or something as subject line. Then I can kind of go through it because otherwise it will be hit or miss. So the same way, like this week we'll do something. And also, remember this can be like your technical blog. That's what really matters when you sort of want whatever to show people that you can do stuff, right? So it's also an opportunity for you to kind of blog about it. You've seen Marina yesterday just mark down the hell out of QGIS. That was a lot of work and it's very elegant, and I'm sure, and she's published it and it'll show up in Google searches. And so you can do kind of the same with your own homework. So you can put as much effort as you want or as little. But yeah. So now let's move into this world. So this is, I don't know, some markdown bug. Yeah, no idea. Okay, so this is maybe the next very important topic. So I won't rush through this. We will stop at 10 and continue after Fika. So this is the library we haven't covered. This is the so we did Spark Core RDDs, and we did Spark SQL with data frames and data sets. And then the second main library is ML, right? Machine learning library. We've seen a bunch of that. And then we also saw Spark streaming, the legacy one, not the more recent structured streaming. But this is basically the other main part of Spark, the other main library of Spark, which is GraphX and graph frames. So let's see. We need to load a particular library, so we should probably get that out of the way at some point. No, maybe. Yeah, so all I've done here is basically an augmentation of this user guide a while back. So these are the papers you really want to look at, and I think this paper is the original GraphX paper. I mean, GraphX is just building on, yeah, so if you want to read one paper about this library, it's probably this one. So let's look at kind of where this is coming from. And as I pointed out, that linear algebra and graph theory are kind of duals in some sense. So you can see, for example, singular value decomposition plus, which is typically seen as a matrix thing, is accelerated using graph methods. And in the same way, this computing the stationary distribution of this random surfer model, which is the page rank, is also doable in GraphX. In fact, that's the sort of more original paper by Google called the Pregal API, and Bagel before that or whatever. So that's this idea of bulk synchronous parallel processing. I think that was before MapReduce. So what we are, so we will get into PageRank, and in only baby examples, and you can literally copy paste the code on the networks we'll build, hopefully, or anything else. Or remember Simon did all this on what we call SNA, social network analysis. He was looking at connected components, right? He was looking at triangle counts and things like this. So all of these, a lot of these, you know, computations on graphs that will not fit into one machine can be done in this framework. They can be, yeah, these specific ones can be done within this very restrictive, relatively restrictive Pragal framework of message passing, where each vertex, each node only passes a message to its neighboring nodes, its out neighbors, you know, who can reach. And then that happens in this main step. And then everyone that receives a message, right? So the guy who passed will also receive, right, from his out his in neighbors, right? So then they take this message and update their state. So they'll have some state that they'll update, and then they will play this game again and again. And then this updated state will trigger a new message, and the message will get passed, and so on and so forth, right? And they receive messages. And then you basically stop the algorithm based on some convergence criterion, like, you know, if the message's state doesn't change by much at any vertex, then, you know, that vertex is done. So then vertices that are sort of reach the stationary state will sort of go quiet and everything will stop. And that's very similar to sort of using matrix methods. Okay, so I don't know. Yeah, this is all good train ride, you know, if you go live in Uppsala and work in Stockholm or something. So yeah, here's basically PageRank. You know, so you have a list of messages, vertex IDs, and initially everyone has, you know, remember I said 0.85 is the probability of just only going to your neighbors, you know, immediate out neighbors, and 0.15 is the probability that this random surfer jumps to any node at random. That's literally here. So that's what's, this is Google's PageRank using this Pragal thing. Yeah, so, all right. Yeah, this is a little bit long, so 15 pages. But we'll just look at some pictures quickly for now. Yeah. So here is the GraphX GitHub. So the main idea is to unify graphs and tables. And if you look at it, you know, the table format is this data parallel format where you have rows sort of work. And then the Pragal GraphLab is gone, you know, fucked. Yeah, so GraphLab is bought by Apple or something. So, but Pragal is this Google's model, and you essentially have this kind of a structure where you have directed edges, some kind of dependency graph. Yeah, let's see. Yeah, so let's. Yeah, and this is the core idea. How the heck do you put a large graph into lots of machines? Well, you have to put some nodes in some machines and other nodes in other machines. Now, what protocol you want? Well, you want a protocol that minimizes communication between machines because of this Ethernet cable problem, right? So there are many ways to do this. Two most popular ways is cutting them by edges. So you can say, I'll cut these edges and put these guys in one partition, or, you know, this is another partition, this is another partition, and, you know, and but then there's this other way saying I'm going to cut a vertex, and, you know, and put this in one and this in one and that. Right? So GraphX uses vertex cuts, and, you know, I think they both have their advantages and disadvantages that these guys use. Yeah, so if you want to get more into details on how the routing works based on these cuts and stuff, you can descend further into this. But we're going to just start looking at creating graphs by our hands and starting to play with some code. Okay, so here is the graph frames user guide. So instead of dropping you into GraphX, we'll start with graph frames, which is like this community package, Spark package, and it's you know, a little bit simpler in some sense. So to do this, we have to import graph frames. So let's see, let's get that import out of the way first. So shared. So let's go to your shared area and create a library. Okay, and let's see, just search for Maven coordinates, and yeah, leave it as Spark package. Oh my gosh. Let's see if something comes up.
Just one word.
Was it one word?
Yeah.
Thanks. Yeah, some weird thing with this. Sometimes I have to go here and.
Yeah, it's a Spark package.
It's in Spark package, right?
Yeah.
But I mean, sometimes it doesn't look for me unless I change it to Maven, search there, and come back. I don't know, some bizarre. Okay, so and I think Spark 2.1, Scala 211. Remember, our Spark cluster should be this for especially later today. So yeah, just grab that one. And yeah, I'm going to close this. Okay, so and also remember, today we want to be running on this cluster. So ooh.
How do you get to the search?
Oh, yeah. So sometimes, like I have to go to Maven, you know, and then search in Maven coordinates, and then come back to. Or you can just do this. You can just yeah. So I have Spark 2.2 here. It should still work.
So what was the Scala 2.11?
Yeah, Scala will be 2.11, but I think just take whatever it is, Spark 2.1. That's what.
Spark 2.1. Okay.
Well, I think that's the latest for graph frames, right?
Yeah, no,
yeah, the cluster, we want the cluster definitely to be 2.2 for later today. But I think the graph frames package 2.1 will still work with it's just all this craziness with osmosis, and I don't know, you'll see. Yeah, so
still get the error. Graph frames is not a member of package org, even if when I created the library.
You have to restart.
Oh, right.
Yeah, restart the cluster.
You have to restart the cluster or detach and reattach the notebook. That sometimes works, but then restarting the cluster is safest. So I think, yeah, so you can do one or two things. So when you create the library, you can say attach to all the clusters always, or whatever automatically attach option, and then you can restart. But later on, I mean, it depends on how much you get into this world, but yeah, you don't want to automatically reattach every time because there may be dependency issues and yeah. Right now it's fine because you don't have a lot. You just have Twitter, Google JSON, right, so far? And this is the third library, right? Yeah. Yeah, those who've already there, please read the graphics paper. Yes.
But do you have to run this in advance, maybe?
No. But you can just run it. Just help. Now what you have to do is just go back.
Okay.
So then just try and create just try and essential. Now we will run over this. And then do one of these instructions. So you don't have to always restart the cluster. I would now imagine reimagine. So let's see if it works because the button we showed. Okay, so looks like so everyone can run those two cells right underneath. Okay, good. Yeah, I mean this is a nice shortcut. Like you can go to recent, and then you'll see all your notebooks in sort of reverse chronological order. So it's you don't have to go and search in here usually. Okay, so now let's try and get our hands a bit dirty. Yeah, so how do we create graph frames? So this is kind of the, yeah, this is annoying. So this is like a too big, right? So this is also good for your blogs. So you know this PNG image is like driving you bonkers. So how do you make this small? So just, you know, you can embed HTML inside this. So you can say img space src source equals, and then do the quote. And I think, is it width? Is it equal? Let's see. Something like this. I forgot HTML. So this will hopefully make, yeah, see, you control the size easily now. Okay, what's the point? The point is, you know, if you're gonna do your homework and have a little more time, and also remember, I'm not in a big hurry for you to submit because a lot of you have lots of other courses, and I guess some of you are making a living, you know, or really working. for the man or woman, you know. So I don't want you guys to rush through it. I'm kind of giving you a template. So, but please put the sort of time you really need. However, my wife will make me go on a vacation for sure. So I think maybe the first week of June is kind of my kind of cutoff. So, you know, you can do these published notebooks and really think of this as an opportunity to actually showcase your skills in data science to your potential employers, right? Especially those who don't have a job or those who want to do more interesting things, right? That would be better for both of us, right? And especially the master's students. Then, you know, I can tell your coordinator, you know, the people, hey, look, this guy knows some stuff. So anyway, I think that would be better because the tutorial is taking too much time. And all right, we're going to create this little Alice, Bob, Charlie, David, Esther, Fanny friend network. And it's a social network. So users can create like graphs. So we need vertex data frames and edge data frames. And vertex data frames have to have a special column named ID, which specifies the unique ID of each vertex. And an edge data frame has an edge with two special columns named SRC and DST, source and destination. So then both data frames can have arbitrary other columns. So these can be various vertex properties, edge properties, and attributes that can be sort of looked into when you're doing your Pregel programs. You know, it's very rich, right? So, you know, yeah. So here's our little baby thingy. So we say SQL context create data frame, and I'm just creating it from a Scala list where I say A is Alice, age 34, B is Bob, and so on. And then here is this other list for the edge, where you see now my IDs that are essentially these strings here, because I say so. I just have to give the ordered pair of strings to define my friend and follow relationship. Yeah. So let's try that. So of course, this is decorating the edge or giving attributes to the types of edges. So, you know, just to put that back into Simon's SNA and combining it with my talk, right? You can immediately conceive of you know, and it's for your potential master's thesis, right? So you can conceive of a retweet network as you know, user ID. A's, you know, column A, source, destination. And then the relationship could be either a retweet relationship or a reply relationship like Simon's Me Too thing, right? So you can have one graph frame representing, and you know, and because of the TTD-DF functions, you can immediately do all the others, right? You can do coded tweets and whatever, blah, blah, blah. So it's immediately can be turned into a graph frame. And, you know, when you do your Twitter experiments for last week's assignment and do something interesting, then you can, you know, do a network, right? Because you can remove, I can also give you little stubs on how to anonymize stuff. And then you can present something, right? Because you guys are a lot of Swedes here, right? Because I have no idea what the tweets mean. I mean, I can Google Translate, but it's horrible. So you can kind of do your own fun assignment, right? So you can find out, as we will see, various things about community structure and so on. So then we create a great graph frame like this. The val G is graph frame VE, right? So vertex and edge data frames go in, and it's so then this. I hope this works. So this is the remember, this is this crazy. It's not that crazy. This is what we used. You know. So this is the D3 package we used, you know, on the wiki click stream thing. It's the same one coming back. So don't forget it's there. Hide code and execute this by this run cell button. So now that should be packed up and ready to go. So if you do, D3 is my package name locally. So it just tells me, it just spits back the help string at you. So yeah, it produces a force-directed graph given a collection of edges of the following form. Source. This DEST, I left it there because I could turn this to DST to make it the same as here, but it's kind of fun to know where you're going from. So anyway, that's it. And then the count is the long, that's the thickness of the edge, basically, right? And it gives you this nice layout. So now I can just, this is a very powerful function, SQL function thing, literal. So this is how you can put a constant as a column quickly, like if you want to put a whole bunch of ones or any literal. That's what we're doing. So what am I doing here? I choose my edges. I go to my graph. I get the edges and I select SRC and DST. But then I rename DST as DEST just because this guy wants a DEST. I mean, I could have rewritten this, but this is good syntax practice. And then I have another column that is a literal of long 1, integer 1. And then I name that as count. Okay, so that's what I'm throwing in to this visualizer, basically, or preparing to throw into the visualizer. So if I do display GE, yeah, let's just make this GE dot no knife. Oh, you did. So I was giving a hard time, Marina, because you or Ebba left the wash knife by the sink, Anyway, I think in maths you don't do that, right? Actually, you either only do that or you don't do that, right? Maths basically is like, maybe not. Maybe I'm exaggerating. Yeah, I think I'm just a lot more paranoid because of my weird school I went to, all the beatings. I don't know. Always worried about things, Now it's illegal to spank in India in schools. So I'm like pretty old. This is mid-1980s. Wow, I don't know. That's a good question. I don't know. That's a really good question. Yeah, I'm sure there's a lot of all kinds of things. All right, but we should maybe discuss that over a pub, when everything is over. Okay, there it is. So we just basically did a layout. Okay. So here is G0. So examples graph.friends. I'm just defining another one, right? This thing is like basically preloaded. So I don't want to just load it for you. I want to roll it from scratch a bit. So it's just it's the same one that's already loaded for you in the examples. Okay, so now maybe let's stop there. It's just 1 minute to 10, and then we'll kind of continue from there.